Have you ever looked at a line on a graph and just, seen a line? Well, today we're going to look a little deeper. We're going to uncover the story that's hidden inside every single line and every curve. It's a story all about its steepness, or, as we call it, its slope.
It seems like such a simple question, right? I mean, you know a steep hill when you see one, but how do you actually put a number on it? How do you say that this hill is precisely twice as steep as that one? Or compare two different moments on a roller coaster ride? Well, let's find out.
So, here's our game plan for today. We're going to start with what slope actually is. Then we'll figure out how to calculate it. We'll explore its different personalities, and then, this is the fun part, we'll see how this whole idea applies to curves, hills, and even the physics of how things move.
Okay, first things first. Let's take that gut feeling we all have about steepness and turn it into a real, powerful mathematical tool that we can use to measure and understand the world around us.
At its absolute core, slope is just this. It's a number. That's it. But it's a number that is packed with meaning, telling us exactly how tilted a line is. You could say it's the secret code of every single incline.
So, here's the key shift in thinking. We go from asking a really general question like, hey, how steep is that, to something incredibly specific and measurable. For every single step we take forward, how many steps do we go up or down? That right there, that's the essence of slope.
All right, so how do we actually calculate this magic number? It's actually way more straightforward than you might think. All you need are 2 points on any given line.
So the most direct way to nail down a line's slope is to just pick any 2 points on it. Seriously, any two will do. Then you measure the vertical change between them and you divide it by the horizontal change. That's all there is to it. That one ratio gives you the slope.
And this brings us to a phrase you've probably heard 1,000 times before: rise over run. It is the perfect, simple way to remember the formula. The rise is that vertical change, the delta y, and the run is the horizontal change, the delta x. This is literally what engineers use to design a wheelchair ramp or figure out the pitch of a roof.
Okay, let's make this super real and put some numbers to it. Just imagine a line on a graph, and it passes through the point 1,4 and the point 2,7. We can use our trusty rise over run to find its exact steepness.
We just plug the numbers right in. So the change in our y-coordinates, that's our rise, is just 7 minus 4. And the change in our x-coordinates, that's the run, is 2 minus 1. This gives us a really simple fraction, 3 over 1.
And that, of course, simplifies to the number 3. That's it. That's our slope. This one number tells us everything we need to know. For every 1 unit we move to the right, this line rises by exactly 3 units. It's simple, it's powerful, and it's incredibly precise.
So now that we can actually put a number on slope, we can start to see that all straight lines have one of 3 kind of distinct personalities. And it all depends on whether that number is positive, negative, or just plain 0.
Okay, check it out. If a line is climbing as you move from left to right, it's got a positive slope. Think about a company's profits going up over time. If it's heading downhill, its slope is negative, kind of like a car's value dropping each year. And if it's perfectly flat, well, its slope is 0. There's no rise at all.
But, of course, the real world isn't always made of straight lines, is it? Profits don't just grow at the same rate forever. So what happens when things start to get curvy? Well, this is where slope analysis gets really, really fascinating.
See, unlike a straight line, which has one single constant slope, a curve has a totally different slope at every single point along its path. So our job changes. It's not about finding the slope anymore, it's about describing the story of how that slope is changing.
Okay, let's try a quick thought experiment. Picture a line in your mind. It's already going uphill, so we know its slope is positive. Now, imagine it getting steeper and steeper and steeper as you move to the right. What kind of shape does that create?
You got it. It would create a curve that just sweeps upward, getting more and more vertical the further you go. The slope isn't just positive here, it's constantly increasing. This is the classic shape of exponential growth.
So with this new skill, we can now basically read the story that's hidden in shapes we see every day, like hills and valleys. Each one tells a complete narrative, just through its changing slope.
Just think about walking over a small hill. What is happening to the steepness of the ground right under your feet at each stage of that little journey?
Well, before you get to the top, you're climbing, so the slope is positive. Then, right at the very peak, just for a split second, the
the ground is perfectly level. That's a slope of 0. And as soon as you step past it, you start going down, and boom, the slope becomes negative.
And a valley tells the exact same story, just in reverse. You start by going downhill with a negative slope, you hit that flat bottom where the slope is 0, and then you immediately begin climbing out with a positive slope. It's this perfect, predictable pattern you'll find at every single peak and every single trough.
So, why is this all so important outside of a math textbook? Well, because slope is the fundamental language we use to describe the rate of change in the real world. Everything from economics to physics.
One of the absolute classic examples is motion. If you plot an object's position over a period of time, the slope of that graph isn't just some random number. It's the object's velocity, its speed. A steeper slope means a faster object. A flat slope means the object is stopped. And a changing slope, a curve, means the object is accelerating or decelerating. Just by looking at the shape of the graph, we can understand the entire story of that object's journey.
And really, that brings us to our final thought. If slope represents speed on a graph of motion, what else can it represent? Well, it could be the rate of a chemical reaction, the growth of a population, or the inflation of prices. The story of steepness is written literally everywhere if you just know how to read it. So, what other stories are hidden in the slopes all around you?